In this video I want to show you how to use the analog to digital converter of your board to make a circuit that turns on an LED whenever a pin reaches a certain voltage. So I have a potentiometer connected to one of the pins, and when the output of that pot gets to a certain voltage, the red LED turns on, and if you decrease that voltage, then the LED turns off. So this is the circuit that I have. I have one of the legs of the pot connected to 3.3 volts, the other leg to ground, and the middle leg to PE1, which will be our analog input. The pot that I'm using is a 50K, but you can also use a 10K or any other pot. This is how the circuit looks on the board. So this is the location for the pins. And a quick tutorial on ADCs. The ADC in the board is a 12-bit ADC. That means that the range is from 0 to 2 to the 12 minus 1, which goes from 0 to 40, 95. And that represents a voltage from 0 to 3.3 volts. So when our ADC is reading the number 4095 or 4095, that's equal to 3.3 volts. You can use this relation to convert between the digital number that you get and the analog voltage. Let's say, for example, that we wanted 1.65 volts. Well, that would be equal to that 1.65, it's half of 3.3. And 3.3 is 4095. So 1.6 volts is half of 4095, which is equal to 2048 or 2048. The resolution of your ADC can be found using this formula. So by resolution, I mean how much does each unit in the ADC represent in terms of voltage. So if 4095 gives us 3.3 volts, then each unit represents 0.8 millivolts. And you can actually also find this formula in the datasheet of the microcontroller. Another thing to note is that in some microcontrollers, you can change the reference voltages. So for example, you can select your 0. So if you want to use something else instead of 0 volts, which is your lowest value, and something else instead of 3.3 volts, which is your highest value, you can connect those pins to the respective voltages. So we see here in this data sheet, that's exactly what it's telling you. It's telling you that this pin is your negative voltage, this pin is your positive voltage, and it even shows you a diagram here. So if we go to the board schematic, just remember this is GNDA, this is VDDA, and that's connected to VREFP, and GNDA is VREFN. So if we go to the board, you will see that VDDA is connected to 3.3 volts and GNDA is connected to ground. Therefore, this value is equal to 3.3 and this value is equal to 0. And that's how I got my formula. And of course, that exact same formula is here. Another thing I want to show you about the ADC in the board before we go into the code. The board has two ADC converters. We will be using ADC1, but these two converters have access to all of the pins, so both of them can sample the same pins or different pins. Lastly, each converter has a sequencer, and each sequencer can sample different input channels. So you can have one ADC used for multiple channels. If you're using SS3, you can do one sample. If you're using SS0, then you can do 8 samples from different channels. And each of these sequencers has its own FIFO where the data is stored. And that's where we'll be reading the result of the ADC. So now that you know a little bit about the ADC hardware, let's go ahead and get started on the code. So if you go to your section 13.4 in the analog to digital converter section, you will see that there's an initialization and configuration section. So if you watch my timers tutorial, you will notice that we had a similar section for that tutorial. So what I have done is I have copied each of these steps and I have pasted them in my code, and that way I can just look at my code and then the data sheet and set each of the bits that I need to set. So the first instruction, or the first step, is to enable the clock to one that our ADC supports. The default frequency in our clock is 16 megahertz. So that frequency is actually supported by the ADC. So we don't have to configure the clock. Next, we need to enable clocking on the ADC module. We're using ADC 1. So if you go to this register in your data sheet, you will notice that you have 2 bits where you can write on that register. And if you set bit 1 then we are enabling ADC 1. If we set bit 0, then we are enabling ADC 0. So earlier I told you we're going to use ADC 1. So I am setting bit 1. So in other words, giving the value of 1 to bit 1 to enable ADC 1. Next, we also have to clock the appropriate GPIO modules. So I will be using port E for my ADC conversion. So I'm using pin PE1. If you recall from my schematic, so that's PE1. That's port E. So this is how I enable port E, and I'm using port F for the red LED. So this is how I enable port F. So I showed you how this register works in my first videos, almost in all of the videos. I'm setting the direction register on E, so I want to make pin E1 an input, so I'm clearing the bit. For the LED pin, I have to make them digital. I have to disable the alternate functions, and I'm making the LED pins be outputs, and I'm turning the LED on. Next, for the analog pin, so for the analog input pin, I have to select which pin on port E I want to use for analog. So PE1, if you go to this register, you will see here that it gives you so whichever bit number you are setting, that will make that pin an analog, or the well, not analog, but the alternate function. And since in our case the alternate function will be ADC, then that will make that particular pin an analog input. So AFSEL stands for alternate function select. So in my code, I'm telling it that I'm using GPIO E, so port E, alternate function select, and I want to use PE1. So if I wanted to use PE2, then this will be a 2 instead of a 1, and that will remain a 1 since I'm setting that bit, since I want to use the alternate function of that bit. Since I'm using PE1 as an analog input, I have to disable the digital functions of that pin. So this register stands for digital enable, and I'm putting a 0 since I'm inverting here into PE1. So I also showed you how to use this register in previous videos. I also have to disable the analog isolation circuit according to the steps. So for PE1 is the one that I need to disable. That's PE1. And I disable it by setting it on this register. So we have configured the ADC. Now we are on to configuring the sample sequencer. Before we configure the sample sequencer, we have to disable the sequencer. So this is how you disable it. Remember that I'm using ADC 1. If I was using the analog to digital converter 0, then this will say ADC 0 instead of ADC 1. So it tells you here that we have to clear this bit in this register. I'm using sample sequencer 3. Let me show you why I want to use that one. So sample sequencer 3 only does one sample. So I only want to sample from one pin. I'm not interested in sampling from multiple pins. If not, I would use another sequencer. So if you go and check out this register on the datasheet, according to the instructions, we have to clear this bit. So that is bit number 3, and that is what I have done in my code. Next, we need to select the trigger. The trigger is what starts our conversion. So how do you tell the microcontroller to begin reading and then converting? You can choose between different options, including continuous sample, or maybe you want to trigger it by software, which would mean setting a particular bit, or maybe you want to trigger it with a timer or with other type of interrupt. So we go to this register on the datasheet. It will give you all the options that you have available. And the option that I want to use is to always be sampling. I don't want to have to tell it when to start sampling. I just want it to continuously sample, but these are the options that you have. This is the value that you have to give the register. So if I wanted to use a timer, for example, I would use 0.5. If I wanted to use an external pin or an external interrupt, then I would use 0x4. I want to be always continuous, so 0xf. So that's 0xf. And the reason why I'm using 12 is because I'm using SS3 sample sequencer 3, and that is where that bit field begins for the trigger select. I'm not using a PWM as the trigger source, so I don't have to do anything for this step. Next, I need to select my analog input. The microcontroller has several pins that can be used for analog input. If we go to the datasheet, there's actually a table that tells you the pins that are available for analog input. So this is the analog input name for the pins, this is the pin number, and this is the pin as it is labeled in your board. I'm using PE1, which is analog input 2. So I give this register the value of 2. If I was using analog input 3, then I would give it the value of 3. In the next step, it says that I have to set this bit, otherwise there will be unpredictable behavior. So let's go check what this register has to offer. So this is the register. I'm using sample sequence control 3. And the bits that I have set are bit 1, which is the one that according to the step I have to set. And I'm also setting the interrupt so that I can use interrupts instead of polling to know when my conversion has ended, and then I will read that value and take action. Depending on the value, I will toggle the LED to either on or off. Next, I have to select the type of interrupt that I want to turn on. So I go to this register, IM. So since I'm using SS3, this is the bit that I have to set, bit 3. So that is where that 3 comes from. Lastly, if you recall, at the beginning of the sequencer configuration, I had disabled the sequencer, so I have to enable it now, and I do that by setting the bit that I had cleared. Then I clear my flags, so I'm clearing my interrupt flags. Then I'm enabling the interrupt. If you recall, in a previous function I had shown you how to make the handler functions. Since I'm using ADC1 and sample sequencer 3, this is the interrupt that I want to make in my C startup file. So I have added that handler function. And don't forget about this line as well. So if you don't know what I'm talking about in this C startup file, watch the video on interrupt vector table and you will know how to add functions to this table. So this is my interrupt function. The function is triggered whenever the ADC conversion finishes, so it's a continuous sampling, but of course each sample starts and then ends, and that's when I retrieve that value and let it continue. So this is where I retrieve the value. The result is saved in this register. So I'm using ADC1 SS3, and then I tell it to continue with the sampling. Then inside my while loop I check the result, and I'm checking for 2048. So if you recall from the formula that I had here, 2048 is equal to 1.6 volts. So what I'm saying here is that if the output of my potentiometer is greater than 1.65 volts, then I want to turn on the red LED. Otherwise, I want to turn off the LED. Go ahead and compile your code, upload it to your board, press go so that it starts, and then go ahead and turn the pot on your circuit, and the LED should be turning on and off depending on the value out of the pot. Another thing I want to show you is that you can actually look at the value that's coming out of the potentiometer. So if you put a, let's put a breakpoint on this line, and let's go ahead and go to view. Actually close this window if you have any open. Then select your ADC result, right click, add to watch. So this is the result that is coming out of your potentiometer when it gets converted to a digital value. Right now my LED is off, so I was expecting this to be as low as it is. Let me go ahead and turn the pot so that it turns my LED on. So I'm going to stop right when the LED turns on. But you actually have to, before you do that, you have to remove the breakpoint and click go. Otherwise, you can turn the pot as much as you want, but nothing's gonna happen since you have actually stopped the code from running. So go ahead and turn the pot until you can see the LED on. So right at that point, go ahead and put the breakpoint again, and you will get a new value. So my LED is on right now, and the value is 2151, which is greater than 2048. So everything is working as I expected. That's it for this video. Thank you for watching.